over dt.
Perfect. Now, of course, this will go away. So now we have to be careful on how we differentiate this piece.
Would it be 2x dx over dt plus 2y dy over?
So 2x plus y to the first power times the inner function prime has to be multiplied.
dx over dt plus dy over dt.
Excellent. That's it. Now I go to this. Now I know what they want us to determine. I will divide by 2v and then eventually take care of this. So then dv over dt, of course I'll simplify both sides by 2. I have x plus y dx over dt plus dy over dt, everything divided by v. I shouldn't even write the v because I don't have v. I have to write the square root of this. So let me write this underneath here. V equals the square root of x plus y squared plus 500 squared. Even if I want to write v here, I don't have it. I have to calculate it. So now, yes, it's okay. Yes, when t equals 900 seconds. Now let's see what I have, and let's see what I don't have. Okay. So first of all, do I have dx over dt? Yes, I do. It's 5. Do I have dy over dt? Yes, I do. It's 4. Nice. But now I have to determine these, x and y. So let's go back. What is x? X is this distance. It's uniform motion, and this distance is covered in 900 seconds. How do I determine this distance? Knowing that the speed is 5. How do I get this distance? Knowing that the speed is 5 and time is 900.
900 times 5.
That's it. So this is 900 times 5. Finally, I need to determine y. Well, this is the y, distance. I know the speed for y is 4, and it's covered in 900 seconds. How do I determine this piece?
times 4.
That's it. Good. So now I'm going to plug everything in and come up with a number. What will be the measurement unit of the final answer?
Feet per second?
Exactly, because v is a distance, and it's measured in feet, and time is time, and measured in t is time, and measured in seconds. So now let's come up with this. I'm going to write it again. Okay. So dv over dt when t equals 900. Okay. So I will factor out 900, and 5 plus 4 is 9. So 8100 times 9 over the square root of, again I have 900, 8100, everything squared, plus 500 squared. I'm not going to waste my time anymore. Just plug it in. Okay, so the numerator is a product. You don't need parentheses, but you know me. Multiplied by 9, and then divided by the square root, and it's 8100 squared plus 500 squared. squared, close. 81, 100 times 9, yes. Divided by, yes. 81, yes, yes, yes. So the answer is approximately 8.98. And you already told me, I'm not going to torture you again. You said feet per second. So what does this mean again? Just to make sure. So the two, whatever, I don't remember, cars, particles, whatever they are, feet per second, I don't know, particles, I guess. So they're going this way at different speeds. And at some point in time, 900 seconds from the moment they start, I say, stop. I shouldn't say stop, but I say, okay, let me see this distance. How fast is it changing 900 seconds later? Now, I don't remember, maybe we should read this problem again. I think there was some sort of was it some 5 minutes later or something? Because if it was, I didn't write that part. I should have read the problem one more time. This was 19. Because if that's the case, then we have to go back. I have to go back and then make some. Yep. So 5 minutes later, a woman starts walking south. So I have to make an adjustment here. Sorry about that. I forgot. I should have read it again. I did not put in writing this. I'm not going to change this. This is okay if they start at the same time. So I'm just going to make a comment here, starting at the same time. But now I have to redo with the 5 minute difference. Okay. So the figure is the same. The formula is the same. So this is still the same. The derivative is still the same. Everything is still the same. It's just that the numbers are not the same. Okay, so dv is still the same as x plus y dx over dt plus dy over dt divided by x plus y squared with a square root and plus 500 squared. So so 15 minutes, again, just to make sure, is it 15 minutes from the moment he starts or from the moment she starts? At what, after the woman starts walking. Okay, so his time is 20 seconds. I mean, it's his time is 20 minutes and her time is 15. Okay, so here we have 20 minutes for y and 15 minutes for x. Okay, so then x is still 900 times 5, but this is 4 times 20 minutes times 60 is 1200 seconds. So this has to change. This is not going to be 900. This has to be 1200. And of course this changes too. But the formula doesn't change. It just hit me that I remembered there was something in there. Okay, so the 900 times 5 is still okay. This is still, there is no change there, so this is still 5, and 4. This is still 500. Just the y changes into 1200 times 4. 1200 times 4. 1200 times 4. So let me see if I can. So this is still 9. This one is not going to be. Yeah, I have to plug them in again. So I'm just going to go directly to plug it in. Okay, so the numerator left. Do I need? No, I don't. So 900 times 5, 4,500 plus 4,800, close, and then times still that's still 9, and divide that. That's still the square root. And I still have 900 times 5, so I have all this. What is this? 8, 9, what is it? 90, 93 squared, and then plus 500 squared. Okay? So am I correct? It's 45 plus 48. Yes, 9,300. So that's it. So it's really 8.99 feet per second. Okay. Good. Other questions for me? Anything else? Anything else that you worked on? Anything else you would like to see? Anything? Okay, so then in that case, let's look at the last section of this chapter, which is 3.10. I'm just opening 3.10. So here we have a couple of topics to look at. Okay. 3.10. Last one. Promise for this chapter and for this test. We're going to look at something called differentials and linear approximations. Differentials first and then linear approximations. So let's go back to our best friend. You can say best friend, yes. We've seen this from the first day of classes. Here's the function. Here's the point. Of course, this is our best friend, point P. And our best friend Q. And of course, this is that tiny distance. This tiny distance. You can say that's age. Yes. But this time we're going to call it, it's the age, but this time we're going to call it delta x. And you can say, wait a minute, you told us that this was delta. Why are you calling this delta? This is the uppercase delta, this is the smaller case delta. So this is the distance, tiny distance between P and Q. Yes, similar to the little age, or they are the same, dx. First of all, let's stop for a moment and let's talk about these two. What are they? And then I'll come back to the picture, to the figure. So when we first talked about the graph of such a function, we said, okay, this is P and this is Q. And how can I explain anything? I can't, because they appear to be so close, right? They are very close. But then we zoomed in and we said P is here and Q is here, but they are still very close to each other. And we said tiny h. Difference between P and Q. P and Q are not the same. So even if they are very, very close, they're not the same, so h is not 0. Okay, so what is this and what is this? So basically this age, if you want, you can call it an error, a tiny error. In other words, Q is so close to P that I can even consider that the distance, the horizontal distance between P and Q is just a minor error. Normally less than 1, right? A tiny error. So delta x then, delta x is the small change. You can say, well, I want to call it error. Fine. In x. So P is here, Q is here, and this is delta x. The small change or the error in x, it is the exact change. No approximation. It's the exact change or error. Okay, what is dx? We've seen dx before, but we never thought that it had a specific significance. It does. It's called a differential. D, the derivative. It's the difference using the derivative. The differential of x. What is it? In this case, it's of course the exact change or error in x. But it's called d and not delta because it's the so-called differential of x. You will see it comes into play with the derivative. This one does not require the derivative. This one is the exact change in x, a minor error between P and Q. But you can say, but this is exactly the same value. True. But we cannot use the same notation. You will see in a moment why. We have to use dx. This one is called the exact change. This one is called the differential of x. Meaning it has something to do with the derivative. Although at this point they are exactly the same. Okay. Delta x, dx. Good. Which is the difference, the small error between P and Q, because Q is not here. Very, very close. But we zoom in because otherwise I can't explain what I'm doing. So this is the delta x or the dx. They are the same. They're not, the names and the definitions are not the same. This is the exact difference or change or error in x. This is the differential of x.